All right, welcome. In this video I want to talk about John Conway's Game of Life and the emergence processes that can be observed within his Game of Life. And if you've not encountered the Game of Life before, it is a two-dimensional cellular automata. So let's take a closer look. So I've mentioned already here John Conway. This is John Conway here. He is a British mathematician and philosopher. And unfortunately, actually, he passed away last year due to complications due to COVID-19. So one of the important losses as a result of this pandemic. And what I have on the right here is just one sort of famous pattern in the cellular automata that, that the Game of Life is. And there are many of these sort of interesting and fun different patterns that form in the cellular automata. And this is called a glider gun because it shoots out these little cool entities called gliders. So before we get into looking more at the evolution of cool things like gliders, let's just define exactly how the cellular automata works. So first of all, like we saw in our last video about Stephen Wolfram's cellular automata, that was a one-dimensional cellular automata. This is going to be a two-dimensional cellular automata. And so we have a grid of cells. And just like in Wolfram's cellular automata, we're going to only have two states for our cells. They're either going to be alive or dead. And as I've done before, I'm going to use black cells to indicate living cells and white ones to indicate dead cells. And I've just sort of arbitrarily colored some alive and some dead here. Although some of the shapes here, I'll point out, this shape right here is a glider. If we were to evolve this, this would move, and this shape here is called a block, and it will actually just stay where it is, and so on. So some of these shapes are special, well-known shapes within the Game of Life. Now the rule for evolution in the Game of Life is going to satisfy the principle of locality that I mentioned again in that last video. The principle of locality says that the next state for a cell should only be determined or only depend upon the local other cells. And in this case, we're going to use what's called the Moore neighborhood. And the Moore neighborhood is going to be the 9 or 8 cells here, depending on how you count it, if you count the center cell in there or not. But at least for the Game of Life, we're only going to be counting the 8 cells around that. We're going to call that our neighborhood, and that's normally called the Moore neighborhood. And we're going to look at that neighborhood and count how many living cells there are in that neighborhood. And we could call that sort of the Hamming weight of the neighborhood, which is just how many there are. We don't care where they are or how they're arranged. We just care how many there are. And our rule is going to depend on how many living cells there are in our neighborhood. So the first rule that I'm going to apply here says a living cell will die if it has fewer than 2 living neighbors. So all 3 of the cells that I've indicated here, this one has no living neighbors. These 2 are neighbors of each other, so they each have 1 living neighbor. But all 3 of them satisfy this rule, that is that they have fewer than 2 living neighbors, so they will die. So on the next step, they're gone. Another rule about dying, then, a living cell will die if it has more than 3 living neighbors. So this center cell that I've got here has 4 living neighbors, and that's sort of an overpopulation situation, in which case this center cell will die out. Now each of the corner cells here also only have 1 living neighbor, so they will die out according to the previous rule. So this shape would actually all die out after one step of evolution. Okay, so we've just looked at some rules about dying. Now, there's sort of an implicit rule there that if a living cell has exactly 2 or 3 living neighbors, it will stay alive. And so I haven't restated that one, but that's sort of implicit in these two. I've said when a living cell dies, so all the other cases must be when it lives. So I'll now go on to the other case. What happens if we start with a dead cell? If the dead cell is born, that means a new living cell becomes alive. A dead cell is born if it has exactly 3 living neighbors. So this center cell here has exactly 3 living neighbors. We can call those the parents in the Game of Life. You need 3 parents in the Game of Life. And then there will be a birth in this cell. But unfortunately, each one of these is an isolated cell itself, so they will all die after this birth. But this will create a birth. And if we went one more step here, of course, this is now isolated and it will die on the next step as well. But again, we had 1 birth in this example. All right, so what I have here is just an example of the Game of Life in one state. I had started this earlier, about 750 ticks ago, and it is sort of settled down into, I sort of think of this as a cooling effect where what gets left over after a number of ticks are just some of these what we call still life, which is patterns in the game of life that will just stay unchanged unless they are affected by something outside of them. Some of these patterns are oscillators, that is, they switch between two states, or more than two states, but most of the ones we see here are two states. And then we also have some just chaotic business going off here still in the center. These are patterns that are still evolving, and they might settle down into a simpler state at some point, but at the moment they're still just engaged in chaos. Now, the game of life is often defined to be have a lot of this chaos going on, but because I did sort of let this run already for a number of ticks, the simulation has cooled down, and if I let this go for a little bit longer, this simulation will probably stop. Well, it won't stop completely, but it will end up in a fixed state where either we just have these isolators, these oscillators that go between two or three different states or oscillate between a different period, and then we have these still life, which we can think of as oscillators with a period of one. They just repeat the same state over and over again. But before, I do kind of want to, watch one of these evolve. There's lots of cool little states in here. But before I do that, I want to do a quick little demo of some of the kinds of life that we might actually see in the game of life. So I started, and this is just a sampling of the life. There's going to be a lot of different life out there that I haven't included here because since 1970, when John Conway invented the game of life, there has been a great amount of research done on the game of life, and all kinds of interesting, cool things have been discovered within the game of life. And so I'm just going to give you a little tour, I guess, of the zoo of all the cool things you could see in the game of life. So first of all, I'm going to start up here in the top left. These 6 shapes that I have here, at least, these are still life, meaning they are oscillators of period 1, if you like, meaning they always just stay in the same state. But let's maybe just look at the block here. This is called a block, these 4 here. And you'll notice that any one of them, they're all symmetric. They have exactly 3 neighbors that are alive, and since each one has exactly 3 neighbors that are alive, they will stay alive in the next step. And we look at this shape here. This is sometimes called a beehive shape. And this one here, all of our cells have exactly 2 living neighbors, and so that's why they stay alive. And this is just the beehive shape rotated. And some of these shapes can be rotated, and I just wanted to show that here as well. This next one here, which is also sort of similar, it's kind of like a beehive, but we've cut out one layer of the middle. And in fact, the way that these beehives work is we could have actually added an extra level, another one in between, make it 3 wide, and it would still have exactly the same still life pattern. And so we could make it arbitrarily sized, and this would just be the smaller version of it, and this has its own name. It's called a tub. This one here is called a loaf, because it kind of looks like a loaf of bread. And then this one here is called a boat, but maybe I can do this here. If I place that one extra little tick there, it creates a new still life, and this one's actually called a ship. A boat and a ship, you can see some of these have names that are related to one another. And in fact, just like the beehive here, we could actually extend the boat or the ship by adding sort of two more little bits here. Let's see if I can do that. I'm going to stop it first so that I don't mess myself up. And starting it back up, we see that, yeah, indeed, this still life will still be still with that one extra bit there, and I could put another one in there. So we could have arbitrarily long ships and boats as well. And again, these 6 are just a very small sampling of the still life that you can find out there. And maybe we'll see a couple other cool ones when we do some simulations here in a second. The next group I have here is these, I guess I got 5 different patterns here. These are oscillators, as I've mentioned. An oscillator is sort of like still life. It will repeat itself, but it will go through some intermediary states before it goes there. So the very simplest one here, and a very common one, is this first one, which we call a blinker. The blinker here is, it just has 2 states, and it's formed by 3 living cells, either vertically or horizontally organized, and they just sort of flip between those 2 states. And again, you can just verify the rules there, why that happens. We've got another one here. This one's called a toad. not sure why it's called. So maybe that shape it looks kind of like a toad. But this one's a toad, and it again sort of flips back and forth between two states. This is another one that flips back and forth between two states. Notice it's formed out of two blocks. This one's called a beacon. And then there's this cool shape here. This is a period 3 oscillator. It takes 3 steps before it repeats itself. And this one, although it's a little bit larger, is also sort of commonly formed out of just random patterns in the game of life. So if you run the game of life, you'll see this shape sort of appear every once in a while. Maybe not as common as some of these other shapes. Beehives, blocks, blinkers, they show up. They're very, very common. But I run the simulation every once in a while, and I'd say about maybe 1 out of 5 to 10 simulations, I'll see one of these appear in the simulation as well. I don't think I've ever seen one of these appear in the simulation, so that doesn't mean it won't appear, that just means it's probably a rarer pattern to form. But this is a period 15 oscillator. This one's called a pentadecathlon, which just means basically 15, or period 15. But it's a period 15 oscillator that will go through 15 intermediate states before it repeats itself back to where it was. But again, outside interference, if there's not any patterns outside of these patterns that come in and disturb these patterns, then they will remain in this state forever. Now, I mentioned this pattern before, but I do want to just focus in on these ones first. These little patterns here, these are the most common spaceship in the game of life. Now, a spaceship is just the name for a pattern that, like an oscillator, it oscillates through a number of intermediate steps, but while it oscillates, it also moves. So a spaceship will oscillate through states, but then also move through the background cellular automata. And again, this is the very simplest one. It is formed out of 5 living cells, and it is called a glider. And so it's probably, I think it was one of the first ones ever found. And it was, sort of interesting. It's like these other lives. These are maybe like plant life. They just sort of sit there and do their thing. This might be considered more like animal life. It can move around and go throughout the environment. Now, when the game of life was invented in 1970, so flashback, 50 years, and you can think to yourself, well, in 1970 they didn't have computers, they didn't have a website that you could just go and watch this happen. So how did this work? Well, in fact, the original game of life simulations were usually carried out by hand, and John Conway, there's some sort of famous photos of him with a Go board, which is a board that you can place black and white stones on, and then he would simulate steps of the game of life by just doing it by hand on this board, which you can imagine was very time consuming. And you could also do it on, say, a sheet of graph paper or something like that as well. But it took until, the 80s and 90s, where personal computers started becoming more common, that we could start running these simulations on our machines and seeing what happened. And indeed, I remember in the 90s when I was doing my own programming, learning at college, this was one of my sort of introductory programming assignments, is make a big giant 2D array and see if you could do some game of life simulation. And so you can imagine, while in those early days, maybe by hand computing these and so on, they discovered this glider. And Conway had put out this challenge to other researchers who were interested in his game of life, saying, well, I've discovered this glider and other interesting shapes. And he put out the challenge, well, could anyone create a shape that would shoot out gliders, that would create these gliders? And that's what we've got up here, this cool little pattern up here. I think it's one of the smaller versions. I think that other guns have been discovered as well. This is now called a gun because it shoots something. What does it shoot? It shoots gliders. And so this is called a glider gun. And this is a special glider gun. It's called the Gosper glider gun, named after the researcher who discovered it. And if I remember correctly, there was a small cash prize, like 50 bucks or 100 bucks, to discover this. And so Gosper and his students went out and tried to find this, and indeed they discovered it. And this was found maybe within a year of the challenge. It was quite quick. And since then, there have been enormous number of other challenges, finding other cool things out there in the game of life that do cool things, maybe produce other types of spaceships, or a real cool sort of result of this is someone said, well, maybe there should be something that creates Gosper guns. What I have here pulled off of Wikipedia here is a screenshot of a puffer type breeder. That's this red thing over here. That what this is like a spaceship, like a glider, but we've zoomed out a lot, so it's kind of hard to see. But this is just this enormous glider that flies through space, and as it does, it plops out of the back of it these Gosper guns, and these Gosper guns shoot out gliders. So again, you can imagine there was a challenge saying, well, could there be something that creates Gosper guns? And I haven't gone down this rabbit hole very much, but I could imagine also that someone said, hey, is there a gun that shoots these things out? And maybe that's been found or not. I don't know yet at this point. But again, these challenges have gone further and further. Okay, now what else did I want to show you in this little demo here? Well, these shapes here, I'm going to start with these two shapes because you'll notice this shape here is actually 4 blinkers. And when the 4 blinkers form this form, they call it a traffic light, which is again another one of these clever names that they use. And the reason I wanted to show the traffic light is because in the game of life, this is a very common formation. The blinker itself is a very common formation, but the traffic light shows up after evolution a number of times. And then same with this formation here. This is formed out of 4 beehives, so it's called a honey farm. And the honey farm is also a very common formation. Now, what we have is sometimes these forms, these common formations, blocks and beehives and so on, these are very common. They are common because some other state before them will evolve into this state. And so sometimes we will give those names as well, like a pre-block, which means the state that happens before a block, or the pre-beehive, which is the state that happens before a beehive. And these ones, this is just my own curiosity. I noticed that these shapes show up a lot in my own simulations, and so I was curious, why do they show up a lot? What were the originating states? What are the pre-states that form them? So I'm going to, let's just stop this now, restart it, and what I've got here are 2 pre-shapes. Now this one, I can't remember, it takes maybe 5 different steps before we get into the blinker. And this one's a little more than that. I didn't count it, but I think it might be more like 10 steps before it gets into that honey farm shape. You notice this kind of looks like just a little bit bigger beehive. And I just noticed this in my own simulations. I said, hey, this shape showed up, and then after a while it turned into that honey farm. And same thing with this one, just by observing it a lot, I sort of figured this out. Both of these shapes could be changed. For instance, I could fill in that center spot, and I think it still works. Let's try it out. Just watch both these shapes as they evolve into their final state. So the left one now is blinking, but the right one's still going, and it's got this kind of cool snowflake pattern that it starts before now it has settled down into that honey farm shape. Let's do it one more time just so we can watch these shapes, because now what I want to do is do a sort of a more massive demo and watch some of the cool shapes that appear as we do. Okay, so pay attention, you'll probably see this shape showing up a lot, and likewise with this one. But now what I want to do is just restart it on random. So when I said random, it's just going to randomly put living and dead cells in there. And you'll notice the very first thing, let's just do it one more time, restart at random, is we got I like to think of this as sort of like the explosion of the Big Bang. We just had a bunch of chaos everywhere, life spread everywhere. And initially those interactions happened, but right away, oh, here's one of those traffic lights forming, but right away, and here's another one of those honey farms forming, right away we see some cooling parts of this, which is where we see states like this, these little blocks showing up throughout. Maybe we got blinkers or beehives showing up as well. This is the cooling of the environment down into these simple states. There we've got the ship formation here, and of course some of these are going to stay, but we see that ship just got devoured by some of the chaos around it. And so what we see here is, even though these shapes are stable, this is still a complex system, meaning they're stable insofar as there isn't any outside interference. But if there is some outside interference, well, we don't know we can't predict what's going to be the case. So this is, again, chaotic evolution, and we can think of these states, like the beehives and the blocks and the blinkers, as attractor states for this complex system. That is, And those pre-states that we were looking at, we can think of those as the basin of attraction for these attractor states, that this block will be formed by all kinds of different patterns that are within that basin of attraction. So now I'm just trying to watch here and see if more of these common patterns are showing up. So we've got one of those traffic lights over here. Oh, something interesting is happening here. This forms a double traffic light pattern usually, but unfortunately it's interfering with this sidewall here. And remember, this is supposed to be an infinite grid, but for simulation purposes, I just made mine a 200 by 100 grid. So it actually has walls that have dead cells all around it, and so we get weird behavior patterns at the edge. Here's another honey farm forming. Here's another honey farm forming over here as well. And we see those honey farms again, like I mentioned, they'll stay where they are, but this chaos on the outside here might come in and interfere and destroy them in a second. All right, I think I'll just speed it up. When we speed it up, we can start seeing things like gliders a little bit easier, and often what happens when we get a glider in here, it's going to float for a bit until it smashes into the wall or into some other shape, causing an explosion. And there's another glider there, hits the wall. But the reason I sped it up is eventually it usually settles down to, yeah, so a state like this, where now we're going to repeat this state over and over again. This is settled down. Now if we had an infinite graph, then it wouldn't just settle down into oscillators and still life like this. It would also have a bunch of spaceships, usually that are flying off into the emptiness. So you can imagine some of those gliders, these little blocks along the wall here were probably formed by gliders smacking into the wall, and so those gliders would have probably floated out into infinity. Let's try it again and just see if more cool patterns appear. Oh, we got a real cool pattern happening up here. Notice this is formed out of four ships, and just like the traffic lights or our honey farms have cool names, this shape here is called a fleet when it's formed out of four ships. This is also a pretty common one. I don't know what the precursor is, or else I would have put it on my demo slide. What else do we see here? Another ship here, a longer boat over here. You'll notice we got some weird still life here near the edge. I wonder if that's because we interacted with the edge, but of course remember the edge is all dead cells, so this is a still life here. Here's another little one here. I don't know what these two are called, but these are special still life. Some of these ones that have, this one I might call a bowl, I don't know if that's what they call it, but these ones, they tend to have other names as well, and that's because still life, sometimes what we like to do is shoot other things at still life, and then it will either destroy the still life or destroy the thing that we shot at it, and sometimes we'll call them eaters, and that's to allow us to do other interesting things with them as well. Let's keep trying. Oh, this is an interesting, like two beehives sort of glued together. I've never seen that shape before. That's another interesting piece of still life here. So now I want to show another little cool demo. There's another challenge in the game of life, which is, can you create something that starts out with a very small pattern like this one? This is a pattern that only has 7 living cells in it. And that will create a pattern that lasts for a long time before it stabilizes into, like we saw before, just oscillators and still life and maybe a few gliders flying off into infinity. We could see often a state like this, we would imagine, would actually just die off. A lot of times very simple states like this just die off in a very, very short number of steps. But if it doesn't die off in a very short number of steps, if it lives a very long time, then we give it another kind of name, which is Methuselah. Methuselah is a biblical name of a biblical character who lived a very long time, and so that's why we give that name to these as well. And this is a very well-known Methuselah called the Acorn. And it will, again, it's only got 7 living cells to start out, and I believe it will go off for thousands of iterations. Unfortunately, because I don't have an infinite board here, mine gets constrained a little bit by the walls, but let's just watch it go here. Again, started only at 7 cells, but it creates a sort of elaborate pattern. And again, this is deterministic, so if we started this with the same 7 cells every time, it will be the same. So that's why this one's very well known. We saw that glider just crash into the wall there. We can see this interference with the wall is going to change the pattern if we had a truly infinite one. But again, a lot of these interesting common patterns that we're seeing: blinkers, blocks, ships, boats, beehives. We've got a traffic light or two. Actually, really cool here, we've got half of a pulsar on the right hand side here. And this is something common when you work with walls like this. You can get half a pulsar because it's like there's another invisible pulsar on the other side there. But I guess it's settled down now here at this state. But that was again another example of what we call a Methuselah, a initial state that will last for a very long time. All right, this was just my video introducing and demoing the game of life. If you're interested, you want to play with this yourself, I have a lot of fun just sometimes just watching these things evolve and the cool living shapes that show up in them. So if you want to do that, I've got a link in the description down below, as well as a link to the code if you want to just see how I implemented this. So thanks a lot for watching, and we'll see you in the next video.